Hello, I hope can you hear me?
Yeah, now I can. I had some. Oh, I just realized the battery of my headphones ran out. I couldn't hear anybody.
Ah, okay,
Yeah, that's fine. Yeah. How are you guys? How are you, Srinivas?
doing good.
Good.
Okay, I
Hi.
think we
Yeah,
yes,
hey, Gato.
I go there. So, um, have anything, Neho?
Yeah, I've been playing a lot with the data, uh, and I shared a Kaggle notebook in the code in the Kaggle channel, in the competition too. One sec, let me see how can I give me 1 second. Just see. And you can still hear me.
Yes, now
Okay,
it's
great.
actually better.
Okay, yeah. Uh, okay, I'll just share my screen. So I've been trying to understand this, some just the data and just um, so it's kind of very interesting problem, right? Like you have different people who are in different spaces. So by that I mean different XYZ, right? And also different shapes and different sizes and all of that. Right? So now, uh, there are a couple of ways to bring the data into like one space so that it's easier for the machine learning model to learn, right? Um, and So I first saw it in one of the notebooks, and I'll show you what I did differently. Uh, I think in this code in the notebook, most words. Yeah, connecting. Okay, so so we all agree with that, yeah, that they should be in the same orientation. Blah, blah, blah. So um, even when all the subjects are in the same orientation, right? Um, Eh, mm, so one of the ideas, okay, so I guess it's an open question is, okay, so you bring everybody into the same orientation, but do you also register everybody to a template? Okay, so by template I mean it's nothing fancy. It's just let's say eh, they had 50, like some group had 50 subjects, MRIs, and they aligned all of them, and they create an average of 50 brains. Okay, so that average is called a template. So in this notebook, what the person did is, um oh, wait, sorry, you see here he picked a reference. Okay, so he just said that I'm going to pick um, yeah, reference. Okay, T1 reference, Control C, find. So every now, wait, where is it? I'll show you exactly where his reference comes from. But remember, shoot, uh, yeah,
He
here.
puts it as readers dot execute, right? Something of just the trainers 20.
Yeah, exactly. So he just randomly picked one patient, okay, and he's saying that, okay, patient subject number 20 is going to be my reference, and that's it. And then any new subject, we are going to align the new subject to this reference, um, and then he just plots. Yeah, so here he takes the first 20, like from 0 to 20, and then just resamples everything to that reference. Okay, or 0 to 19, right? And then 20th one is the reference. So takes those 0 to 19 and aligns them to the reference. And in the end, he says, um, yeah, you can also resample into coronal plane or resample into this axial plane, but using another patient as reference, right? So when I was just uh, and I don't know, I think it's so I think just experiments will show like, okay, is it better to take everybody to a reference or just once you align? So aligning, bringing them in the same plane or all the four like T1, T2, that's for sure. I think that definitely makes a lot of sense. But this, um, do you align to a reference or do you just keep them in the original space they were in? Um, so when okay, so then
But what is it? Sorry, Mehul, what is it that the reference is actually doing? I still don't get
okay,
what
I'll show
I
you.
mean, I understand the alignment, but what is the reference to a single patient doing, and how can you? Uh, wouldn't it be first still necessary to get the plane alignment? How can you refer when the plane alignments are all different?
Right. So yeah,
Let's say the 19.
mhm. Go ahead. Yeah.
Let's say the 20th patient you pick is axial,
Right.
and we saw that the 19 patients, or if he is doing for 19 patients, or is it 19 slices? Uh,
19 patients.
and
Oh, okay.
okay, so then each of those patients could be, some of them could be coronal, some sagittal, some axial. Then what is the reference doing, and
Right.
what is even a single, when he says, is he just reading reading the 20th image, and then what does the reference do?
Sure. No, absolutely right. So like say let's say the reference was axial and the other images are coronal, right? So before you can even do the alignment, you need to bring it into that. You need to make it axial. So change the alignment. And I was just trying to see. So his function is called resample. Um, that is where is resampler? Yeah. Okay. So resample, basically we can walk through this code. It takes the image and the reference image, and it says, okay, we are okay, a reference image. Um, you so there are these. So the planes are decided by the transforms. So you can set all the get all the parameters from the reference image. So basically what happens is at the, let's say you start with coronal, but and your reference was axial. At the end, you will get you will convert your image, coronal image also to axial, and more importantly, everything will match. Let's say the sizes were different, so you match it to the reference. You match everything to the reference size. So it will be one. Let's say reference was 128, 128, 128, and your image was 150, 150, 150. You basically mm, make sure that you bring your 150, 150, 150 to 128 cube. So resample takes care of, so that resample function takes care of all of those steps. I think it even takes care of like the voxel spacing. So suppose the reference was 1 by 1 by 4, and your image was 1 by 1 by 3. Yeah. So basically, now you have pre-processed your images so that all the images are in the same plane, and they are also of the same size. Does that help a little bit?
Yeah, no, that does. But then how is that different from what we have already done? For
Yeah.
example, I mean, this is one approach from what has been done, for example, in the voxel approach, right? And in fact, you know, unless we dig through the code and find out that this guy, you know, has what I liked about the voxel approach is the fact that in that case, what the guy does is, let's say for all of the images, right? Meaning for the entire image in our training set, for he takes the for any given image, he takes the dimension, the x or the y or the z, in which it has the most pixels, right? In which the density of the pixels is highest, and then uses that to, what does he do? To kind of normalize with or to adjust it with respect to the other images.
Right. Yeah.
Right. Yeah. In fact, he says that in the, that's one of his comments, right? He finds out X, Y, or Z having the biggest, and then uses that to sample, right? Because that's the way that you would get the best result of a voxel when you're creating, voxels for all of the different things. So unless this guy is using a similar approach, right? If he's just picking at random the 20th image and not choosing the, like we don't know that the 20th image is the one which has the best X or Y or Z, right? It could have any X or Y or Z as I showed in the EDA.
Right, yeah.
Right. So if he's now regularizing with respect to that image, then that doesn't guarantee that you're getting the best XYZ or the worst XYZ, depending on whichever way, like it's just randomly picking something and then standardizing it on that.
Right. Yeah. No,
you see what I'm saying?
No, yeah, absolutely. Yeah. So, yeah. So, okay, I'll answer that. Yeah. So, definitely that he's picking that subject at random. So that's not ideal. Right? So I was just looking at that direction a little bit more, and so what I saw, and I'm not saying like this is the best way. I'm just seeing how people are pre-processing the data.
Right, approaching. Yeah.
Just different
no,
approaches.
Good to know all the different ways. So,
yeah.
And again, I'm just making the point that he might also be doing it. I'm just saying that we would have to look for that, right? Meaning like, how is he choosing to whatever we want to use the term for? How is he choosing to standardize regular? Is there a medical term for what the voxel guy did, where he used the pixels, the most dense pixel dimension, and he used that to normalize or to whatever, extrapolate?
No, it's so in the medical term, like we many times we have this concept of atlas. Okay, so atlas is nothing but let's say you took 1,000 MRIs from India, right? And you take the average. Okay, so then you can say, okay, this is the average brain of, like, say, 1,000 Indian men or 1,000 Indian women, and you will, and let's say you took from Japan and Germany, and you will see.
One sec. Sorry. Even before you go to the next step, let's stick with that step because I want to understand. When you say average, right? Do you assume that the X, Y, and Z dimensions for each of the MRIs that you're averaging is identical, or if not, what adjustments do you make?
Yeah, it could.
You see what I'm saying? Because that's
yeah.
important for me to get how to average, right? Because if the thickness is different for the different brain images, then if you need to do something before you average them, right?
Right. I think people, let's say your best resolution was 1 by 1 by 1, right? And your worst resolution was say 3 by 3 by 3. I know people use resampling, but I don't know, would you, maybe you pick your worst and then you bring everybody. I'm not sure. I should look that up, how they make the atlases, but they, I think they average, bring
Because
everybody.
if I would imagine you can take one of two, like you're saying, right? You can bring everybody to the least common denominator, meaning, like whichever is the worst resolution, you bring it to that, and that's all you get, and then you average. Or you could go the other way, in which case you're kind of maybe generating some noise or some additional information, because you would have to take, you go to the highest common denominator and extrapolate pixels for the worst resolution, for the worser resolution images.
Right. Yeah. Yeah, I was just trying to quickly see if I can find that. So sometimes when the competition we have, because it's like brain tumor, it's from different hospitals, right? And it's different machines, different hospitals, and they have very different resolutions. But like in this atlas, they just scanned at one hospital, so they didn't have that issue too much. But I'll look a little bit more into like whether they downsample or upsample, even if they have different resolutions. Um, so okay, so basically, let's say a normal brain looks like this, right? Where you can so where you can see the detail of every structure, and this is one of the subjects from the competition. So just to show you, this is the on this side is the atlas. So there is some, you see, there is some, there's some smoothing. Because after taking the average, you get something like yeah um, so that's what the template is. And I'll Srinivas, I'll just finish the one approach I saw, and then we can compare to the voxel approach. And so, so they the basic the basic idea is like, we uh, take the four images you have, the T1, contrast, T2, and flare, reorient them to uh, to a specific orientation, and then okay, what's the best way to say this? So they did so they have two steps. Okay, this is finally the end goal is to get all the images, all four images, all subjects into this one atlas space. And what does that look like? So here I actually have the contrast images of two different subjects. I actually downloaded a few more just to show 535. don't know. One second. Yeah. The mouse is here. Okay, let me take another subject. Okay, so these are, just click here. These on here, what you see is these, oops, these are 4 different subjects. Okay. And okay, you see this small structure here. Okay, just think like can I zoom? No, how can I zoom in? I don't know how to use this.
I can see it.
Okay, yeah. So okay, maybe I can do this. Okay, so this, okay, you see this Mickey Mouse, right? So what this Atlas thing has done is that this Mickey Mouse of all the subjects is now in the same location in the array. So as I scroll, okay, now I'm in another subject. It has a slightly different Mickey Mouse shape. It's not, yeah, it's maybe, so this is another subject. This is, or maybe these two are the same, that's why. Okay, I probably loaded the subject. Yeah, that's one place. Maybe even this branch, maybe it's easier in this brainstem. So if I click here, why doesn't it? See, all the structures are aligned. So, and if we load if I do the same thing with the voxel data, like that voxel approach, everything is 128 by 128 by 128 or whatever, right? 64 by 64 by 64. But the like the structures won't be in the same place. They will be in like slightly different places. You see what I mean? Like this is only possible because we have aligned everything to the atlas. Otherwise, this wouldn't happen. And so what I don't know is which does it matter for deep learning? Like if you
yeah, let's even before that question, and let's assume it does, because that, it obviously, in some sense, you're saying, well, yeah, that's one question, but the to me, the other kind of relevant question is, or two questions is, I should say, are, one, why does when you resize the images, why do the structures not align? Is it because of the way that the MRI is taken, that you don't end up, when you resize job and all that you don't end up with the structures at the same location? Or what is, or looking at it from the other side, what does this process do, quote, in the alignment that the voxel process does not?
Right. No, great questions. Yeah. So yeah, because all those patients were in different MRI machines in different countries, right? So there is no way to say that that the origin, like say let's say my matrix is 256, 256, 256. There's no way to say that, okay, I want this Mickey Mouse at location in the center of the matrix, right? I want it exactly at same. I gave the example of 256 cube. So my center of that cube is 128, 128, 128. So I was like, there's no way to make sure that different people will be in the same spot, or structures will be at 128, 128, 128, and that's one thing, because just they are in different scanners, different countries, and even so, what he did is he first cropped it. Right? So let's say originally they were in different spots, and then he cropped it, and then he did a resize to 64 cube, right? I actually have some of those images. Should I just download it? And so that's why, because of the there was no step there to realign it to some common template. So that's why those structures don't line up in that voxel approach. Um,
So what you're saying is that if there was this additional step that supposedly this method is going through of quote this alignment,
right?
Then the alignment shifts the brain image so that it would have to shift the image, right? It would have to move the pixels around, right? But as a group such, and you could potentially only do, isn't it the case that, I should ask it as a question. If you, let's say you have two parts that you get, when you're aligning, then you have different structures within the brain, right?
Right.
I don't know, I'll just pick two, they may not be relevant, but like a cerebellum and some other structure A and structure B. Let's not even name them, right? Like brainstem and something else.
Yeah, brainstem and cerebellum.
So because one of those is the brainstem, right? The one on the left.
Yep.
So now, if suppose you are doing this alignment, then I would imagine that you would need to move groups of pixels by different amount. Is there like a set of groups that you pick, or how does the aligning thing work? Because if I want to align my cerebellum as compared to my stem, I might, and if I want to do both, then I might have to shift one set of pixels one way, the other set of pixels the other way, and then anything in between will have to get interpolated and stuff, right?
Right. No, you're absolutely right. So in this case, in this alignment, these images were just generated with something called a three-dimensional rigid alignment. So we don't make it as sophisticated as you said. Like say we apply some translation, then the brainstem and the cerebellum get the same amount of translation in XYZ. So there's something called like nonlinear registration, where you would apply different, I think they call it like deformations. So they apply, and we are getting into like 3D data processing, and but this
correct, yeah. But alignment, basically, you're saying in this case it's rigid in the sense that you pick one thing to snap to. Does that mean you just pick one entity to snap to?
Let me see how many degrees of, what did they say? Rigid registration to rigid registration. And here, they have a translation, and so translation X, Y, and Z, and rotation in X, Y, and Z. So they have 6 parameters like that. But that works surprisingly well. So what's a good way to talk about it?
Okay, so you're just saying that assume that, I mean, we can, I guess, dig into the detail to figure out how they do it, but that's essentially the difference that you're pointing out between this approach
and the
voxel approach.
Right.
Okay, and the pending question. I mean, you could potentially apply the same registration to the voxels. I don't know at what stage in the process, and get the same result, right?
Yeah, definitely. Even we could take his output and just apply the registration. That should still work. Yeah.
Right,
So
right. Because either way, I mean, it's just an additional step, but where you have to apply the step, I don't know. There might be a proper place to apply the step, which is an open question that I don't know the answer to. Meaning, do you do it, after you have converted it and after you have kind of snapped to the lowest common denominator, up sample or down sample, or before any of that, you first register, or you first do this registration and then you up or down, where it appears in the pipeline. Do you know the answer to that?
No, I don't. So I just know that this pipeline is from the guys who made the competition, or well, I don't know. So it's a little confusing. So it's basically a toolkit, right? You see my webpage, right? So it's called the brain tumor pre-processing pipeline. Okay, and I don't know. I mean, but it seems pretty like it's a big NIH funded group, and they made these. This pipeline is exactly for the type of data we have. They say that you have 4 data sets, okay, and they've figured out some things like, so because there are 4 images. This is the last thing. Then I'll just talk. What they decided is that, okay, you take the contrast enhance, so that one has the biological information about the tumor, right? Like the tumor spreading and stuff. So they said, okay, let's register the T1C, the contrast image, to the template, and everything else is registered to the T1CE. And then, so you have two transformations, and then they apply. They came up with this pipeline. But like you said, you could do this different ways. You could crop, do the voxel approach, and then do it. But this is the pipeline they had. Yeah. And the last thing I wanted to mention, so like whatever pipeline we use, we have to run it during inference. So what I was trying is, so for example, these people, they released a binary, released a Linux binary to do these steps, and what I figured out is I only need till step 2D, and they have something like skull stripping, but our images are already skull stripped, so we don't need to do this. And they also have tumor segmentation. So right now I haven't run this, but basically this pipeline aligns everything and then segments the tumor also. So I skipped these 2 steps, and I just wanted to see, okay, if we want to use a pipeline like this, can we run it in a Kaggle kernel? And that was painful, but I finally managed to get it to. Come on. Yeah, so I just made a small notebook where you can ignore that, where I just took one of the test images to see if I can run this pre-processing in the Kaggle kernel, and because also there is a time limit, right? So I was trying to and then this is how you call it. It's pretty straightforward. So I have I give it the DICOM path of each of the scans. So T1C, T1 weighted. These are my 4 inputs, and that's where I wanted to store the output. And then I just call it like this. So this, so I did it for one subject, right? So it one practical thing that might not allow this sort of pipeline to be used is there enough time? Because I couldn't find the time limit for the inference. Like we have to predict on all the test images in certain fixed time, right? So if one subject took that much time, I don't know. Is there a better way to time like how a command? I thought time was enough, but it's a little confusing. It tells me that the CPU time is 35 say milliseconds, and no, the total time is 63 seconds, but the wall time is 4 minutes. So I'm not sure which is the right one. But basically we'll run into issues like this. Whatever pre-processing pipeline we pick, it has to finish in the allocated time. And here there is some more stuff like, so what was painful was I had to take the binary, and so I made the binary into a data set, and then I did some stuff like I'm actually install. So I had to install like a module, like one Linux module was missing. And yeah, basically this is how I figured out how I can install this binary on the Kaggle kernel. Yeah, actually I learned a lot in this because it turns out it's an Ubuntu. The Kaggle kernel is based on an Ubuntu machine. It's Ubuntu 18, and I had to so this was the installation, for example, and then there was, so in that Linux environment, you can get the path with os.environment, and then I had to add the path of the program I installed, and yeah, all these steps to yeah, but it's possible to like install like Linux binaries in the kernel, because I think that's what I wanted to. So we will have like, okay, one is which way to go, which way to do pre-processing, and then does it finish in time in inference? Okay, I think that's all I had for.
Interesting. But you were able to do it, though, is what you're saying.
Yeah, I was able. Yeah, I think what I need to try is, if I see, I don't know the public test set is 87, right? Um, do you know the size of the full test set? The hidden.
Yeah, I mean, they kind of give you the, I think they say something like it's what we have. I mean, don't take my exact, you can go to the, they say 4/5 are in this is 20% and that's 80%.
I see. Okay.
So if, and I think we have if I recall from memory, I think we have the public is 87. Is that correct?
That's right, 87.
Right. So if you assume, that's 20%, then so
yeah,
the overall is 400.
Okay.
Right.
Okay,
So we are talking about having, so there they say it, right, that 5x the size. So it's, so if this is 90, that's 450.
Okay, got it.
So that means if you are processing at, I mean, I don't think that the wall time is the correct measure. I think the total time probably is. I'll have to check. But your total time was what, 60 seconds or?
60 seconds, right.
Which is, let's say, a minute. So that itself would mean if you have to run it for the inference, then that takes an hour and a half.
Wait, 450 minutes, right? Oh yeah, for the pub, right?
Oh, sorry,
hour and a half
sorry.
for the
For the 80 90 for 450, then yeah, it's 450 minutes, which is
yeah, I couldn't
quite a bit, right?
right,
Close
yeah.
to 8 hours. I don't think they give you that much time.
Okay.
If you look at what they tell you with respect to the time thing, I think they do provide some
Code requirements.
limit, right?
Oh, less than
Yeah.
9. Oh, crap. Okay.
Yeah.
Yeah, I'm already.
So if 8 hours are taken in just the data thing, then all of your rest better happen in less than, like, I don't know, 30 minutes or 45 minutes.
Yeah. Yeah, which might not have. Yeah. Okay. Yeah. See, then okay, this is good. Good. We check this. Yeah. Following though. Okay, I can GPU notebook. Okay. Yeah. Okay. That's I see. This is good to know. Yeah. Yeah, because one thing I can with that binary that that what you guys were talking about, right? Like it also has somebody already trained like a deep learning based segmentation model. I haven't run this part, but I can run. Actually, I can just run because the way I turned it off is I just said lost it. I just there's a flag. You just say segmentation off. So I just turn the segmentation. But this would give you. It would do the registration and the segmentation. See, it does both things for you. And this is what I was asking the organizer that they talk. They have a paper about how they prepare the data for the competition. So I was telling them, why don't you just release the all the normalized data to us? Because we are spending so much time in image pre-processing rather than the deep learning thing. And but I think he didn't reply back to my question. Yeah.
Yeah, I mean, it is significant. I mean, you could argue almost, or not all, but many of the things are data prep exercises as much as they are any other technique exercises. But that's somewhat true of many competitions too.
Right. Yeah.
So, but yeah, I mean, if they already have it and if they've done it, then I don't know why. But maybe they're looking for some other approaches or. And the other question is, is it easy to, or is it, or how to do this last bit about registering?
Yeah. No, absolutely.
Right.
Because because some people might have like the domain knowledge, so they like they might have all like somebody who's working on brain tumor segmentation, right, as part of their PhD or work. So they already know the pre-processing steps, like which is the right way to do the pipeline, when to put the steps. So they get they released a paper on how they prepared the data for this competition, and they said they did this, and in fact, yeah, that's where I got the idea, because I saw in the paper that they said they registered to the anatomical template and then they did this, blah blah blah. Yeah. Any okay, that's it. I think that's what I had right now. Yeah.
So I guess the term that, in fact, you just mentioned it. So the process step missing in the voxel approach is this registration to an anatomical template, which means
right.
Snapping your image to some fixed, snapping some, and that's the part that I'm still somewhat unsure, snapping one or multiple of your anatomical entity to some location some standardized location which is there in the reference template.
Right. Yep. Mm-hmm. Yeah, you try to align
Right.
as yeah. Yep.
Right. And the alignment, what I can't yet determine for sure is it of one entity or multiple? Because if you are saying multiple, then you will need to do something more complicated. If it is just one and then the others are approximate, then that's fine, right?
Yeah, I think they
Either
just do
case, you would have to do some matrix multiplication and some pushing around of pixels.
right. Yeah. I'll try and see if I can find. Let me actually let me just. Normally, these guys have a really good education. Okay, I look for this co-registration, like some nice videos or descriptions about it. Education.
And by the way, the next or the second, which is very relevant question that you had raised, and I would like to hear multiple people's opinion since I have been yakking, maybe others should chime in too, is the question you raised, which is how important do we think it is for a classifier to be able to determine something,
right?
And or how easy or hard is the determination of the classification if the entity I don't even want to say the entity that we are classifying is in different locations, because actually it's not even the entity, right? It's the quality of the entity that we are trying to classify. Because the entity, because again, let me step back. When I use the word entity, I mean, it's like saying we are, first of all, in reference to our current problem, what we are trying to decide is whether from the image of the tumor, we can decide something about the quality of the tumor, because it's an attribute of the tumor, whether the MGMT is 1 or a 0, right? So from the pixels relating to the tumor, we want to determine whether the tumor is of has some particular characteristic like MGMT1 or MGMT0. So to me, that's equivalent now to saying, first, let's say that there are dogs in the picture, and do the dogs have spots, right? And if they have spots, then we have 1. And if they don't have spots, then they are, like 0, let's say. So the question that, to simplify and abstract it away from all the brain stuff, the question to ask is, how important is it that the spots, that the dogs be in some fixed location to make it easier for the classifier to pick whether the dog has spots or not?
And
And when I phrase it that way, then reacting to my own phrasing, it seems like if your classifier is, first of all, if you apply segmentation and if you don't apply segmentation, 2 instances. So if you apply segmentation, which means you're now narrowing your focus to the pixels where the tumor exists, because that's what segmentation helps you do, then I don't know that you really care whether because your tumor is going to be in different locations within the brain, right? They are not going to be in the same location. So if your registration, all it does is it puts the tumor in some location, right? But the tumor itself can vary in different locations in the brain. Then what have you accomplished by snapping the image to the same location? If I were to ask to cast an opinion, I would say it's irrelevant. Right? But now, if you don't check, do you agree?
Yeah, when you phrase it, when you phrase it like that, it's the position shouldn't matter. I just need to see, like some of the tumor segmentation pipelines, which are not doing, which are just doing segmentation, they have been aligning to the common space, but I don't know why. But I can try and find out like why are they doing the segmentation pipelines use this as a pre-processing step of aligning everything to one space. But yeah, I mean, it's not clear exactly why. Like if they just ran experiments and they.
The segmentation.
Yeah.
Interesting.
So because so for example, I show you 4 subjects here, right? So one thing is all of them, none of them have tumors in the brainstem and cerebellum. So you see, like I'm just scrolling. So this is one patient. Where is his tumor? But basically, there's no. Yeah, see, it's right in this part of the brain. That's where the. So this person has a tumor here, but nothing in the brainstem and the cerebellum. And this subject, nothing here, but he has it. He has it in the front of the brain. Yeah, right there.
Right.
So I don't know if it's helping the segmentation, but I thought it's, again, I'm not sure. Like, if the
it might help segmentation. I haven't thought of whether it does that. But now, if we don't use segmentation at all, then it then again doesn't the same. Now let's think through. So we are not segmenting, or we are not like focused on just those pixels, which as a first pass, it seems to me that what we're arguing for is it's critically important to apply segmentation before we classify, which we all, I think, would tend to agree with that statement, right? Because otherwise, there's a tremendous set of pixels that you are processing, which are all overwhelming the negative, because all of that is negative anyway. I mean, first of all, they don't have the relevant pixels, and then obviously they won't have this MGMT stuff anyway. So I think we are processing a lot of noise, because it's like saying a dog is in one corner of the image and we are looking for spots on the dog, and then there's like 90% of the image doesn't even have a dog in it.
Right, exactly.
So shouldn't we be first segmenting the dog and then looking for the spots within the dog?
Right, yeah.
Right. But but if we don't apply segmentation, then again, the same thing applies, right? Meaning like, why is it important for the dog to be in a particular location in your image? Or if the location of the dog varies, does it matter for finding the spots?
Right, yeah. And
but I think that argument falls apart in this particular brain case. In my own, I'm kind of arguing against myself here, but primarily because I think the relevant object first needs to be identified, which is this tumor. So I think the question comes down to, as you said, why do people, if they are using it in segmentation, meaning if the registration is important to segmentation, then it just boils down to, hey, why is it important in segmentation to register?
Right, yeah. Yeah, I'll try and find that for next time. I started looking at, there's just too many papers. I'll make a Google Doc.
I kind of, in fact, there's too many concepts about medical imaging to learn for me to begin with. So I was like, okay, I'm just going to try to simplify.
You know what? One thing, one crazy thing I saw is, like you said, we have to segment the lesion. So one really interesting idea is you use deep learning to segment the lesion only, okay, but then you use traditional image processing and machine learning. So you segment the lesion with deep learning, then you try to extract properties about the lesion with traditional image processing, and so those are your features, and then you put it into like SVM or maybe even in just a regular neural, like a neural network, and try to classify it. So somebody released a like there's one notebook where they do segmentation, feature extraction, and then classification. But yeah, not do it with a CNN, but do it with just a dense neural, do the classification with a dense neural network, or even a XGBoost for that matter from that point. Yeah.
Right. Now, how do they extract features?
They point to some package like so the simplest features are the mean or the median intensity, right? So you could think about, okay, the simplest features are what is the mean intensity here, what is the standard deviation, and then they have some features like texture, like what is the texture of the tumor. I think they even had shape. Shape could be an important feature, right? Yeah, so they released like they link to a Python library to extract features, right? Called
Oh, is that a public notebook?
yeah. Let me just quickly show you. One second. Yeah, this one. Yeah, so he talks about, yeah, that's how we did the registration. Following segmentation, he used some unit segmentation algorithm, right? And yeah, this is the
Yeah, there are multiple. By the way, there are multiple segmentation stuff. Segmentation.
yeah
3D
right.
models available.
Yeah.
Which, by the way, I had a question on that. Did you find any good 3D classification models beyond this EfficientNet, which seems to have all kinds of problems?
No, not yet. I saw. Okay.
Because I was looking and there are some, but I don't know. I just was, there's notebooks pointing to some, so I spent some time, but I haven't yet started to use them. So I was just curious because obviously based on what you already submitted and ran into problem, and then the guy seems to, if you can pull up where that you talked about, oh, I'm not maintaining, I'm just using this.
Yeah.
So sorry if it's giving problems. So it doesn't seem like that's a good 3D supported, this EfficientNet TTorch Pi thing.
Yeah.
That doesn't seem to be a reliable model.
Right. Yeah. No, I'm in the same place right now. Yeah, I don't think that's reliable. I didn't see anything else yet. Yeah, I just saw this guy.
If you find anything, I am chasing a few pointers. If I find it, I'll post.
Okay.
And if I'm able, because it's not just finding, it's also the fact that you have to be able to, it should be, you need the source and stuff, because you need to be able to reach into it and modify the head, right? Like we do with this case, right? We need to reach the last layer and strip it out and stick in a fully connected layer that goes from whatever the output of that layer is to a single output, because we just need true or false.
We should, sorry, Srinivas, I just saw one thing, sorry. So this notebook, right, he talks about that PyTorch, but then he doesn't use it because this is like a TensorFlow and Keras, but we could do the same thing in PyTorch. So you see what he did? He just built his own model. He just said like, but yeah, this is not pre-trained, but then he just, he just built like with a bunch of, and this syntax is the new TensorFlow syntax, right? So it's called, instead of the sequential API, it's called the functional API. So you say X, you have to pass the input, the previous layer as an input. So X is a convolution layer, and then to max pool you pass X like this, and you just keep going like that. This might, and then you basically add your own, but then this is. He just made his own. That was confusing. I was wondering. I remember he was doing in TensorFlow. So why is he referring to the?
Yeah, I mean, we could, like you said, just use that. I mean, there's no reason we can't create the equivalent in Python.
Yeah, I think he got
one.
Yeah.
Right.
Validation accuracy is okay. Yeah, that's all. Yeah, that's what I had so far. I'm mostly looking at the data and.
Yeah, no, that is. I mean, it's almost 90% of it, right? Because the classification is just a matter of kind of deciding a 1 or a 0. I mean, it's not like going to be that.
Right.
So I think the focus is absolutely the right one of getting the data thing figured out.
And that notebook, right, where they, I think this is a one. It's going to be the notebook where he did registration and then segmentation and the feature extraction. This one. He used a 3D segmentation model, but he has a lot of examples where the 3D segmentation failed. So this one, you see all of like this is the 3D segmentation output, and then it's outside the brain. So then I think he did some cleanup, like, okay, just look for out. That was one. Yeah, I thought some of them were interesting, like the 3D seg. Yeah, so we'll have to be careful about that. Like, this one is a nice notebook because he does.
One request here, if you can post even just the couple that you referred to in the Slack, not in the chat, but in Slack, that would be great.
Okay, I'll put it in Slack.
Just a few that you were pointing to.
Yeah.
I just wanted to add something.
Yeah, go ahead.
On the alignment thing, like I think it does not serve any purpose, right? If you're using convolution-based methods, since convolutional architectures are like translation inequivariant. I don't know what it's called. Invariant.
Yeah.
So like all you're doing in convolution is just you have a kernel and you're just moving it around the whole image, right? So it does not matter like where in your image the actual region of interest is. It will be found wherever it is, right? So I think it does not serve any purpose if you are snapping all the images, if you're snapping a particular entity to the center or something like that.
Yeah, it shouldn't matter.
Yeah,
but
that's kind of what I was trying to say, but I think Gautam stated it more technically precisely and gave the reason, right? Because I was trying to say if the dog in the image is on the left or the right or whatever, and you're trying to find spots in the dog, it doesn't really matter where in the image the dog is.
Yeah.
And as Gautam stated it, the reason for what I said is the CNNs are kind of location invariant.
And I just wanted to understand, like, what is the difference between the voxel approach and the one that Mehul was showing? Like,
yeah, so basically in the voxel approach, he just cropped everything. He basically removed the non-brain areas. Okay, so so the brains are of different sizes, right? So after cropping, maybe one might be 50 by 50 by 50, and the other one might be 75 by 75 by 75, 75, 75. Right? So after cropping, you will get different sizes. So the last step he does is after cropping, he does a resizing in that notebook. So that was because I was just,
okay, it's specific.
Yeah, if you can pull that up, we can point to the particular point that I was saying, which is a good thing he does is he chooses the dimension which is the most, if I remember correctly, and then
he I'll come to that, and then, but here basically, wait, where is his pipeline? His pipeline is, yeah, you see, we change it. What happened to the cropping?
No, in this particular thing, maybe is
Oh, wait, this was, maybe he was showing, yeah. I think somebody was complaining about it. Okay, this one. Yeah, so he want to get everybody in the same size, right? These are different subjects, and where was his? Oh, sorry, it should be above this. Yeah, there you go. So you get the voxels, so get the volume, do some normalization, crop, and resize. And in one of them, there is that step what Srinivas was saying, which dimension?
resize, in the resize.
In the resize, okay.
If you look at the resize detail, if you go up.
Okay.
Yeah.
Okay. Yeah. Yeah, and NP argmax, right? Yeah. Whichever shape is the, yeah, you
Whichever
resize.
dimension of the shape is the most, he then resizes based on that.
Right.
And he says the explanation is there on the top, right?
Yeah, yeah. Sample planes are.
Sorry, was there a question? I cut off.
Yeah, I was just wondering if that resizing was just padding it with zeros or
No,
interpolating.
No, it's actual resize. So it's cv2.resize. So
okay.
Whatever the size, you resize it to, like, say 64 by 64 or 128 by 128. Yeah. So you're doing some interpolation.
Okay.
Yeah. See, the point being that, and let's use the thickness to explain it, or at least in my head, it's an easier. Let's say X and Y are the same, but you get different thicknesses for the different images, right? For example, but if you have different thicknesses for different images, but now you want all of the images to be of the same thickness, 64. Let's stick with 64 by 64 by 64. But obviously, the last dimension, meaning the Z dimension 64, is different for all the different images. So some are 64, some are 128, some are 256, and so on. But you want to make all of them the same 64. Now, you have two choices, right? As Mehul was mentioning before. You can go from, you can kind of upsample, or you can downsample. And that is, you can start, and in this case, what he does is he takes the largest dimension along, and I'm sticking with the example of the Z-axis, but he actually does it for any of the three axes. And in the Z-axis, which is the depth axis, if the largest you have is 256, then he's saying, I'm going to take my image, which might only have a depth of 64, map it. So he's interpolating or extrapolating additional pixels in the Z dimension to the 256, and then snapping it to 64, and then cropping it to 64, right? The other way he could have done it is he could just have said, I'm going to take the 256 and downsample it to 64. But that's not what he's doing. He's taking the dimension, the max dimension, which for this example, let's stick with the dimension being Z, and the max being 256. And using that as the reference, snapping all lower Z dimensions to that by interpolation, which is what this CV2 resize does, and then snapping it back to the 64 by 64. Right? And as he also says, the perfect way of doing this is to do it twice, but he just does it once. Does that help?
Yeah, that explanation helps. Yeah.
Right, and obviously he's doing it along not just the depth, but he's picking which of the three is the most. And I had a notebook I shared a week or two back, or showed that there's a whole variety of X and Y and Z dimensions in these images. So there's some of them have like 25 different dimension values. Some of them have 17, some of them have 19. So each of X, Y, and Z vary quite a bit. Also, Mehul, what I did was, Mehul and I offline were chatting over the week of some of the things that I found. I can just very quickly share. If you have a few more minutes, Mehul, do you need to drop off or?
Yeah, I'm listening. Yeah, you can just share. Yeah.
Okay. Let's see. Share my screen. Okay, let me know whether I'm confused. So let me know what screen you see. Do you see the one saying BC loss?
Yep.
Okay. So let me go to. So this is the notebook that Mehul had shared earlier last week about the kind of the notebook that we were playing with to get the process working using the 3D efficient at PyTorch. But maybe if Mehul is, Mehul, you can share a little after I'm done the issues, the issue that you saw with it, right? Which is that it was giving, once you submitted, then you were getting all 0.5 kind of results. And so I'll kind of point to a few things as we go along that I thought were interesting or at least relevant, and also share something which lead me to suspect that this efficient net model has some issues, right? So one of the things this guy does is, obviously the pre-processing is the voxel processing that we have used here. So you'll see that. Now, Mehul has made some edits to make sure we can just run it on one particular type, and I kind of stuck with that here. One question, Mehul, did you try, I kind of commented out because I wanted to use all of the voxels. Were you able to try with slices, and did that improve your score? Because I thought this is your attempt at kind of choosing slices within the image, right?
Right. I did that. Right. So, yeah, because I wanted to I loaded all the data sets, 64 by 64, 128 by 1, like the 128 cube and the 256 cube. And I noticed like if I tried the 256 cube, it was running out of memory. So then I saw, so yeah, this all I did there was take the 256 cube and take the middle 128 slices. So you leave 64 on each side, and then you just take but no, I didn't. I don't think the validation scores were all about the same. Like 0.61 was the highest. But then whenever I submit, whatever I did didn't matter. I think I did 10 experiments.
Yeah. No, forget the submission part, because that seems to have an independent problem, right?
Okay.
I was just wondering whether your AUC scores improved.
No, not really. It is all everything was around 0.61 or 0.6. I didn't see a big difference.
Okay. The other reason besides running out of memory to do this, right, is also the fact that by doing a variant of this, you are somewhat, I don't think it's analogous, but what you are doing is eliminating slices which may not have any tumor in them, right? Because a lot of the initial and the ending portions of your image voxels don't really have tumor related information, right?
That's right. Yeah.
If you go back and look at the EDA and of some of those things, you see tumor doesn't show up until at least on the bottom of the image. It's not like most of the tumors, as you showed, Mehul, are in kind of like certain sections of the image and not in certain sections. So by slicing, you're kind of reducing the number of pixels that don't contribute towards the classification, or the analogy would be slicing helps to reduce the pixels which don't have dots.
Right. Yeah. Exactly. Yeah. And some people, there are some really nice notebooks, so they figured out in the X and Y they kept like 256 by 256, and they resized it to just 32 slices. So somehow there's a couple of other like parallel notebooks going on where this voxel approach was 64, 64, 64, but there are some other approaches which are like just take fewer slices and be done with it. Yeah. Maybe we can look at them next time.
Yeah. So that's a good point. Yeah, that's worth trying. But you could also try 32 slices within what's been done here. Right?
Yeah.
There's nothing that prevents it from using 32 of, and after scanning through a bunch of images, we can decide whether the 32 ought to be taken where, depending on your orientation or something. Right.
Yeah. Right. There are a lot of experiments to run.
Yeah. So, and then Mehul kind of did, the reduction elimination. That's what this is. But the few comments I had is, see, he has this label smoothing here, right? And I have it as a task to do because I don't think the way he implemented label smoothing in the notebook is quite correct. But then he does something which eliminates this label smoothing effect. So I just wanted to kind of get to that and see whether you guys agree with respect to my interpretation. So keep in mind that what label smoothing is kind of reducing the confidence in the 1 and the 0. So basically you kind of, make the 1 values less by 0.01, which means instead of being 1.0, it's now 0.98. But the zeros is where I have a problem with the way that he's doing label smoothing. But then I'll also get into why eventually he doesn't do any of label smoothing at all, I think. Here's the part where he overrides the parameters to make the output features 1, which is what we want. Then this is just a matter of training. Here's one thing, Mehul, that I saw, which I fixed, and I wanted to hear your thoughts. While he's computing the valid AUC, if you look at this code, right, then he actually, and it's confusing, but if you look at the reference notebook that Mehul had pointed to, this was commented out by him already, and then I commented out this code. Now, if you look in the highlighted section, he's choosing the validation loss to determine the score, okay, and not the AUC. Right. And I was just curious whether, so I changed it to actually use the AUC.
Okay. Yeah, that makes sense,
right?
actually. Yeah.
I don't know why he was using the loss versus the actual score. And what was even more confusing is he reports this as AUC.
Yeah. Yeah, that's
and
a bug. Yeah.
It's not AUC. It's actually the loss here that he is reporting.
Right. Yeah.
Right. So I kind of fixed that.
Yeah, that's good. Yeah.
Because this is what we care about, right? The AUC, not the loss.
Right. Yeah.
Right. So that's one change. But the other thing I wanted to point out is this part. And I wanted to I finally think I figured out why he does it. So in the validation, he has two values, right? So Y is the target and outputs is what we generate as outputs. Okay, so he does the notart, the targets, outputs, blah, blah, blah. Then he comes here and then he does this step. So Y all is 1 if X is greater than 0.5, L 0 for X in Y all. And this particular step, I was confused originally because AUC, he takes from sklearn to be just the ROC-AAC score of Y all and outputs all, which is just, comparing all the targets to the outputs we generate. But here is the issue, right? Here, he has actually applied this thing to convert all of the targets. And, again, I wish he had used something else because here the X doesn't refer to the X in our data set. It just refers to an element in Y all. But bottom line, he's just converting Y all to ones or zeros. So I was like, why are you doing that? Because your Y all itself could be, ones and zeros. That's what we have. Except I think the reason he's doing this is this particular step nullifies any kind of label smoothing stuff that he has done before, right? Because in label smoothing, you would divide the one or you would subtract the 0.01 from the one, and then you would make the zeros have very small positive values.
Yeah.
You see what I'm saying?
Yeah. I mean, now that that's good. You caught that. I'm not sure ROC. I was just looking at the ROC function in sklearn. So that threshold of 0.5 is very arbitrary, right? Like.
No. But here is the important thing, Mehul. The thing is, he's just doing this to the targets, which if you don't even need any of this if you didn't have the label smoothing marking around. You could just have left the targets alone to be ones or zeros.
Okay, I see.
You see what I'm saying? I mean, he's doing it in order to nullify any, even though he gave himself the option of doing label smoothing, but he doesn't want to use label smoothing right now. I mean, you can come back and introduce it later, but because he somewhere, I'll look at it in a minute and maybe I'll find out, but somewhere he changes the targets to be, you know, he uses the label smoothing to, yeah, here, you see this? Okay, here it is. Look at what he does there.
Srinivas, he might be doing it just for the purpose of calculation of the ROC AUC, right? For training, he might be using
No,
the actual label smooth ones.
No, because you see the, here is, and I'll get to what Mehul said, which is if you look, at least my understanding, and we'll go there next, which is look at what sklearn label smoothing actually does. Because my understanding after looking into sklearn label smoothing is that you can just give it a couple of values and it will figure out. It doesn't have to be explicitly 1 or 0, or, and it doesn't, you can give it probability values on your output, and you can give it some, again, number corresponding to the range between 0 and 1. That's my belief, and we can confirm that in a minute. But if you look at just this, and I think I have a problem with this, but I'll confirm whether it is actually an issue or not. I haven't gotten the time to dig into the detail of whether this is a correct implementation of label smoothing. I believe it is wrong, but let's just look at it in the form of if it is 1, what happens, and if it is 0, what happens. So if self.target index gives you 1, then he does the right thing, because all he is doing is 1 minus the self.label smoothing value. The label smoothing value I just showed you is 0.01. So if my target is a 1, then he gets a 0.99 as the Y value. Do you all agree?
Yep.
Right. Now, on the other hand, and this is where I have a problem with it, is on the other hand, if your self.target index is a 0, then it will be 0 minus the 0.01. But that's why he takes the absolute, because then it will become 0.01 instead of negative 0.01 for the cases where the target value is 0. But here's where I think I have a problem, because I recall from the FastAI label smoothing example that I think he ought to divide this by the number of zeros that exist, because if that's my recollection, but I could be wrong. I know that in the case of value 1, what you do need to do is subtract the label smoothing value. So you make it 0.99 in this case, because you have given the label smoothing of 0.01. But I think, and I could be wrong, if somebody else knows better, if Gautam you recall, or Mehul, whether this absolute of taking this so that all the zeros become 0.01 is the correct way to do it, then let me know. I seem to vaguely recall that that is not the correct way. You have to divide by something to make, so it's not just every 0 is not just 0.01. Every 0 is 0.01 divided by the number of zeros that exist. That's my recollection, but I'll double check that. But now, so you have the values of Y are not ones and zeros, but they are ones and they are 0.99 and 0.01s, right? Now, so if you don't want them to be 0.99 and 0.01, but you want them to be 1 and 0, then what he does here will work, right? Because, sorry for all the scrolling, but let's look at, where did I miss the part where he was doing the X? Oh, it's after that. It's in the, here, right? So remember that our voice were, 0.99 and 0.01. If you do this, then all you're simply doing is snapping all the 0.99s to 1 and then all the 0.01s to 0. That's all you're doing, right? So I thought then that all this statement seems to do is nullify what you have done in label smoothing before.
But does that come after the training is done or before? I mean, if it's after the training is
It
done, then
comes,
it's just for the purpose of ROC AUC calculation.
it's done only when you calculate ROC AUC score. So when you are, like when, so when you're calculating loss,
yeah, go on.
yes, when he's using the, that's a good point, that when he uses the targets, he's using the targets as 0.99 and 0.01.
Yeah, so he's not.
But when he's using, then even less makes sense, right? Because now let's look at what sklearn actually does. RAC AUC score. Right. So Y true, Y score. Now Y score can be probability estimates and non-thresholded decision values. Right. So in fact, originally, Gautam, to your point, I thought that the thresholding ought to be done on the outputs, right? But this seems to say that you don't need to threshold. You can just give it the probability values.
Yeah, but the label smoothing is just for the training purpose. When you calculate the metrics, you should use the ones and zeros that you have, right? Why would you use label smooth values for the metrics? That doesn't make sense. Right?
But it doesn't matter, right? Because if it is if it is going to compare and
but that label smoothing is just for the purpose of making your training a bit more robust. While calculating metrics, it doesn't make sense to use that. And
so you're saying
even in your public leaderboard, the ROC AUC is on the ones and zeros. So ideally, you should also do the same thing while you are doing your calculation.
Okay. Yeah. So you're saying it's not that he has undone label smoothing, it's the fact that he has to undo it in order to do the ROC AUC score properly.
Yeah, that's what it looks like. Yeah.
Okay. Yeah. So I was puzzled by why that line of code, but it makes sense now. But it's also interesting that sklearn scoring doesn't require, this was somewhat confusing, but it doesn't require you to threshold the scores. I thought that you would probably want to supply the Y score after you have applied some level of thresholding. But it says that
yeah, no, that acts on the actual probabilities. Yeah. So you don't have to threshold on your the predictions of your model.
Output.
You give it the actual prediction, and this score is actually calculated independent of whatever threshold you use. So that's why this is considered as a superior metric. It does not depend, like if you do accuracy or even F1 score, it depends on what threshold you have chosen, which is usually 0.5. So it depends on that. Whereas ROC AUC is independent of whatever threshold you use. Yeah. And then you can also, another advantage of ROC is you can also choose the best threshold by looking at the diagram. And yeah, you can choose the point which is having least false positives and true positives.
Right. You can, that's the other thing I was thinking of, right? That you could, if it seems to assume a particular, but you should be able to plot and then figure out for your results what is the threshold to apply to the output so that you get the best AUC score, right?
No, the AUC score is independent of your threshold. It is just dependent on your model. In our case, we just want a good AUC score. So we don't have to, there is no choosing of threshold at all. It is just the area under the whole curve.
Okay.
There is no step in which we choose any threshold. So later on, if you are deploying
Because
your
it's
model,
independent of the.
yeah. It's in actually the curve is generated by choosing a range of thresholds from
Right.
0 to 1. That's how the curve is generated.
Yeah, that's right. And just to add to that, so that's what confused me. Like in the notebook, it says greater than 0.5, right? So he could have just passed the whole vector without doing those greater
No,
than
Mehul,
0.
that y is the actual targets. It's not the label. It's not the model predictions.
Okay.
Yeah,
It
it's
is
the target.
Yeah.
Hmm.
You are not doing the thresholding on the predictions of the model,
Okay, I see.
which is outputs all,
Uh,
I guess. So you're not doing thresholding on outputs all. You are doing the thresholding on the
on the Y-out,
yeah, on the actual targets given to
which
you.
is the target. And I think now I agree with what Gautam is saying, that I was confused by thinking about it as a threshold. Actually, all he is doing is fixing it to be the target values instead of the target values, which because of label smoothing is mucked with when using it in the training and validation loops.
I see. Okay.
And he's just returning it to what it was originally. Okay, that makes sense. But this line confused me terribly as to why he was doing it. But anyway, that's the reason now I agree with the correction that Gautam provided. I'll fix that. But so then, as you run this, and one of the things, Mehul, that I wanted to comment on is, if you see the loss reduces and the training loss has gone down, but look at the validation loss, it's fairly significant. And the thing which also is troubling to me, which is why I thought that the 3D model seems to have some problems, is you get some scores. I still don't hit 0.6. It's like 0.56 something, 8.9, blah blah blah.
Right.
And then I will come to this particular point as well, because I in the middle of figuring out all this MRI stuff, I think I lost my bearings on my basics of classification, so I have to go back and look at that. I'll get to my confusion in a minute. But so you predict and ensemble, and in our case, we are not ensembling, we're just using one MRI type. And you see the thing which to me was, you see this output and you see the values.
Yeah.
They're almost exactly the same. They only vary in the 4th decimal.
Right. Yeah. Yeah.
That
maybe.
seems strange, doesn't it?
Yeah. I think something is wrong with this.
And by the way, and by the way, just to switch to so I did it for each of the 4. I'm see, so this one, it says flare. So I ran it with the flare type of image. Now let me switch, and you see it's about 0.504, but it's 0.504 for every single test image, which doesn't seem to inspire a lot of confidence. But now, if I look at this guy,
it's all 0.59.
it's different, but it's exactly to the 5th decimal.
Yeah.
That doesn't give me a lot of confidence.
Mm-hmm.
Right? That implies one of two things, that either the slices, and I stuck to 128 by 128. So either, without segmentation, we are overwhelming the classifier to where it finds no meaningful thing because we are giving it so much negative. But, or, there is some fundamental problem with the network, with the model that we are using, right? Because it's just exactly all the same.
Yeah.
So that's why, as I said, I'm in the hunt for a different 3D model.
Yeah, I think you're right. We should shift to something else. Maybe just make our own model. I couldn't find any pre-trained models.
Yeah, and I'll post if I see anything because I did some digging, but not enough to bottom out on the model. One other thing, while I have you folks, that I wanted to kind of, as I said, I kind of suddenly lost my bearings on some basics. So I kind of set it aside that, okay, I need to figure what I'm doing wrong, or at least something in my understanding or the way. So, like I said, this is just a binary classification problem. Like there is 0 and there is 1. So it's just a question of, I think, so I thought that now let me show you what is the loss that he uses. So the criterion that he uses is okay. The criterion that he's using is this guy, right? But since that's just a binary 0, 1, I thought we should be able to use cross entropy, right? Rather than binary cross entropy with logits. Does that make sense?
Yeah.
Right. But something I think now, so initially I switched the binary cross entropy with logits to cross entropy. And then I tried to train, and it gave me this error.
Oh. Yeah, that's.
I mean, I set it aside to move on, but anybody, I haven't dug into it deeply, but anybody.
Yeah, the difference between cross entropy with logits and normal cross entropy is that softmax step, right? Where if you do softmax on your own, then you use normal cross entropy. If you don't want to do that softmax step, you can just set the loss as cross entropy with logits. So that softmax step is kind of embedded into the loss itself, so it's a little bit more efficient. So yeah, if you have your own softmax loss, then you use the normal cross entropy. If you don't have softmax, you have to do the with logits loss.
Okay,
that's why
so
the
basically,
expectation of
yes.
different. Yeah.
Okay, so you're saying that if I need to add log softmax to, no, well, actually it does the NLL loss. So I guess I don't have the need to do the log, but just need to do the softmax
Yeah. Right. Yeah.
myself.
Yes.
Okay. Okay. So that was the other thing. I was just playing around, and I was like, oops, what did I do wrong here? And I'm going to go back, to the code to see what you just summarized for me, Gautam, which is need to take the softmax, which happens automatically when you do the thing with legits. Because I tended to remember it differently as, okay, if you just need, multi-label thing, then you use this stuff. But you're right, it's also because of the presence or absence of the log softmax inclusion within the binary process. Okay, got it. Thanks for the clarification. Okay, so that's it, and which kind of points to, we need a different 3D model.
Yeah.
So maybe we can discuss all that next time.
Yep, that sounds good.
Okay, great.
Okay.
Thanks, everybody.
Thank
See you all next week.
Yes, see you.
Thank you. Bye.
Thank you.